So today we're going to finish floating points, like floating point numbers, and we're going to finish this integer number. That's the hope. Let's see how much we can. All right, before we start, is there any questions about the course, homework, or anything else? Okay, so let's just start. So I stopped here last time. So before, now we, because last time we covered rounding, right? So we basically learned how we can represent floating point numbers, and we also dealt with the issues of rounding because we actually have limited precision. Somehow, we have to pack them into the limited number of bits, right? So that's the issue of rounding. And now we will move on to the, okay, let's do multiplication first. So let's move on to the arithmetic for like a floating point numbers. The first one is about 녹음 잘 되죠? Okay. The first one is about like a multiplication. So if you successfully completed your like high school education, you probably know how to do this like a multiplication in scientific number format. So let's think about an example in like a decimal number, which you already know, hopefully. So we want to multiply the two numbers, something like 3.14 times 10 to the power of minus 4. Okay, that's number one, like a number A. Second number is B. Let's say this one is like a 4.00 multiplied by 10 to the power of 2. Okay, so how you do the multiply? How do you multiply these two numbers? You know that, right? So if you multiply these two numbers, it's A times B. So what we do is we calculate the multiplication of this part, right? So if you calculate it, it will be 12, like 5, 6. Okay, and then the second part, you simply multiply this part as well. But now we only do addition for this like exponent, right? So it's, in this case, this one will be 10 to the minus power of 2. Okay, so hopefully you already know how we do it. And then because we want to re-normalize this number to the original like a scientific format. So in this case, this one now have like this one is greater than 10. So 10 is the base. Because it's a decimal number, we actually have base of 10. Because this one is greater than 10, we actually shift this number by one digit to get like 1.256 times power 10 to the power of minus 1. Okay, that's the answer. Right? You already know this. The idea is exactly the same. Just we do apply the same idea for the binary numbers, binary like floating point numbers. So as I said before, generally two numbers are represented in format. There are three fields: sign, mantissa, which mantissa is basically significant, like significant digits, and exponent. Are represented in this format, and then calculate the multiplication of the two field by field. The first sign field can be easily obtained by taking XOR of the two, right? That means if any of the two number, if either of the two number is negative value, then we're going to have the result will be also negative value, right? So that can be represented by this XOR. The significant part, like M parts, as we did before, we simply multiply these two numbers, right? And the exponent, this part, we simply add these exponents, like two exponents, to get the final, exponent number. So this one is pretty easy. And after we do that, we need to do some like a fixing. So if this number, like M, is greater than 2, because now we're talking about base 2 numbers. If this one is greater than 2, we actually have to shift this number shift right by 1 bit, and then we also have to increment, this. We basically adjust the exponent part, right? And if the E value goes out of a range, meaning that if it becomes larger than the maximum number you can represent, then it's because basically it's overflow. Finally, you may end up having like more bits than you can pack in this like M field. Then in this case, you actually have to do some rounding to actually fit them into like some number of bits. So it's kind of very straightforward. Hopefully what you already know. Implementation-wise, the biggest chore, like biggest like a task in this like operation is like this part, like multiplying this. That's kind of the most expensive part of this floating point operation. Otherwise, the other like calculating XOR or calculating addition is kind of easy ones, right? We apply the same idea for like floating point addition because you know how to do it. So let's take the same number as an example. Let's say 3.14 times 10 to the power of minus 4 plus 4.00 times 10 to the power of minus 2, 10 to the power of plus 2. So if you want to do the add, what do you need to do? So first, you actually have to align those decimal points, right? So if you, let's unfold this number. So this one is something like 0.000314. Okay, minus 1, 2, 3, 4, right? So this one, if you unfold this number will look like this. And if you expand this number, then it will look like, this one will be like 400. Right? So in other words, before doing the addition, you actually have to first align these numbers to the same decimal points. Okay? And in generally we actually align these two numbers for the number having the higher exponent value. So that's the convention. So if you, let's say we assume like we had two numbers, number 1 and number 2, and assume this E1 is actually greater than E2. So in this example, maybe like this one is E1 and this one is E2. Then we first align these two numbers to have the same like exponent value. Then in that way we can just calculate the addition of these two like significant value, right? So we first convert this part to actually have the same exponent, like 10 to the power of 2. Okay? Then what should this number be? Like 3.14. It actually should shift by how many bits? 6. 그죠? 6자리죠. Because the difference of digits is like 6, right? So we actually have to shift like this, like m parts by 6 bits. Then it will be 0.0000. I don't know. I may be wrong. Maybe this is 314. This one looks right to me. Okay, so it'll look like this. Now, because now we actually have the two same like exponent, now we can simply add these two m. Then that's our result. Okay, so so basically we first align these two numbers and we do like addition for this m like field, and then we do some like a rounding or like shifting or something like renormalizing the number, right? That's how we do. So fixing part. Because even though I took this like a binary number as an example, but the same decimal number as an example, the same logic applies for binary numbers. Okay, the only difference is base is now 2 instead of like a 10. So if you want to fix this, once you do this like addition, you may actually still have to do some fixing. If m is greater than 2, then you have to shift m to the right and increment the value of e as we did before. And if m is less than 1, then you actually have to shift you have to shift it to the other way, like the other direction, to actually we always start the first like digit with 1, right? So we basically that's kind of normalization. We normalize the value to actually follow the original format. And overflow and rounding is the same as before. Okay? Overflow may happen as a result of addition, or rounding may be necessary as a result of addition, right? So this will actually apply is the same as the previous one. So let's think about mathematical properties of a floating point add first. So how this floating point add compares to abelian group. I don't know how many of you know like a definition of abelian group. So this one actually is this one is extra slide. So this, by the way, for those who are not familiar with like abelian group, this one is definition. So definition of abelian group is a set, in this case, set will be the all possible numbers that can be represented using like a 14-point representation, right? That will be the set, right? Set together with some operation dot. Let's say the operation is dot that combines any two elements A and B to form like another element. It's a function. This dot actually takes two like elements in the set, and then it map it to the like a third element. Okay, so if this like set and operation, let's say A and dot satisfies the following 5 requirements for all possible A and B and C, then it's called a abelian group. Okay, so that's the definition. So there's a set and there's operation, and this like operation actually takes 2 elements as input and generates a 1 output element. Okay, it's like a mapping, right? And then if that mapping actually satisfies all these 5 properties, then that's called abelian group. So the first property is closure. Let's say, you can actually, we're going to apply this idea for like a floating-point addition. So you can think of it like you can think of it as an addition, like add this operator. So closure is the result of operation A dot B is also within the set A. Okay, it's like a close. Okay, in the set. And second property is commutativity. So commutativity is A dot B is always equal to B dot A for all possible AB pairs, right? That's the second property. And third one is associative. associative가 우리말로 하면 결합법칙인가? 그죠? commutative는 뭐지? 아, 교환법칙이구나. Okay, thank you. So second one is commutative in 교환법칙, and third one associativity is 결합법칙. So if you want to calculate, taking A dot B dot C is equal to B dot C and doing like a dot A. So the order of computation doesn't really matter in this case. That's the associativity. And existence of identity element. So identity element is like 항등원 in Korean, right? So if you do some like take an element and do this operation over some element E, then you always get the same original element. So this one is 항등원 in Korean, right? And the last one is inverse element. So if there's for like each like element, there's like another like element which actually basically if you apply the operation, you obtain the identity element. Okay, so these are like a property, 5 properties that must be satisfied by any like abelian group. Back to the our like a floating point numbers plus floating point add. So whether this an operation forms an abelian group or not. So the first question is closed. The answer is yes, because you take 2 floating point numbers and do add, then you always take some like number which actually falls within the floating point set, right? So it's closed. Commutative. A plus B is always equal to B plus. So the answer is yes. If you find any counter example, please feel free to suggest. But as far as I know, there's no example. So hopefully you're okay with this. Third one is associativity. A dot B dot C is equal to B dot C dot like plus like you can change it. The answer is this one is a very interesting part. This one is no. The floating addition is not associative. Why? Because I can show you a counter example. So this one is one like counter example. Let's say this one's A, B, and C. Let's say this one's A, B, and C. Okay? In this case, depending on the order of computation, the result are different. So in the first case, let's say, B is much bigger number than A. Okay? So let's say this one is, we take this like a decimal number as an example, but generally, this pattern actually holds true for binary number 2. So let's say in this case, B is, 10 to the power of 10. It's like if you expand it, it looks like 1 0 0 0 0 0 0 0 0 0 0 0. 1 2 3 4 5 like 10 zeros. Don't count it. Just 10 zeros. And this one is relatively very small number. This one is 3.14. So if you add these two numbers, the answer will be 1000000000003.14, right? So if you do the add, but let's say this number is too wide to fit in like bits in M. Okay, so then it'll be truncated. It'll be like we're going to lose some valid digits, right? Because now this number becomes too big, right? So let's say we can only hold like 9 digits in like a decimal number. Then we only get like this part, but we're going to lose like whatever follows. So if you compute like this number, and we're going to re-round, like normalize this number, we end up getting the same, like 10 to the power of 10, like this. Because we lose some because we don't have like enough bits to pack like entire like a valid digit. Okay, then if you then you actually take off like the same number, then the result will be 0. Okay, but what happens? We compute like a b plus c first, the second part. Then in this example, these two numbers are the same, although they are really big numbers, but they are exactly the same. So then now we can just they cancel each other. So they cancel out each other so that this one becomes 0, and now we end up getting 3.14. In this case, this one is counter example. This is an example that shows that when these two expressions actually result in different numbers, different results. So from like this example, we can conclude that this floating-point add is not really associative, which actually has some important implications if you do some scientific computation, right? Sometimes, let's say you do like a simulation for space. I mean the stars, and make it like a space mechanics, like the force between some particles or like stars and so on, right? Then actually depending on the order of computation, your result may vary. So actually you have to be very, very careful when you deal with this kind of computation. So the fourth property is 0 is like additive identity. So now we in this set actually has additive identity. And finally, every element has additive inverse. This statement is almost true, but not always true. So almost, why is almost? Because for any positive or negative, like a normalized, denormalized numbers, then you actually have like a additive inverse. But if you actually have not a number, infinity, then there's nothing. I mean, there's no additive inverse. If you add something to infinity, then you always end up getting infinity too, right? Or not a number. So this is true except for infinity numbers. Likewise, monotonicity, if A is equal to or greater than B, then A plus C is equal to or greater than B plus C. That statement is also almost true. Not always, because the exception is an infinity, not a numbers. Okay? So in conclusion, a floating-point number, I mean, this a floating-point number, set of floating-point numbers and floating-point addition does not form an abelian group. It's not. Okay. What about the point multiplication? Let's compare this one to commutative ring. So now we introduce another concept. So commutative ring is now we actually introduce a set. Likewise, let's say we have a set, and we have two operators. So we define two operators. Let's say that operators are plus and dot. Okay. So now these two operations are something like multiply and add. Okay. So now let's say we have some group, and then we define two operators. Let's say plus, addition and multiplication. Then this set and two operators form a commutative ring if this addition actually is like a, I don't want to be too much detail about this, but let's say this one's abelian group plus forms of abelian group, and for this like two operations, distributive law actually holds. If those two conditions are satisfied, then this one is called like commutative ring. So now we actually have to not only for not only for this individual operation must be a group, but it also should satisfy this like distributive law. 분배 법칙이죠. So 분배 법칙 is something you already know that, right? A dot B plus C is equal to A dot B plus A dot C. So this one is like a distributive law, right? So if this condition is satisfied, then this set plus two operator form a commutative ring. Okay, this is the definition. So let's say, let's think about, this, do the same exercise for this floating point multiplication. This one is also closed. The multiplication is closed but may generate like infinity over n. But still, if you take any like element, any like a value from floating point representation, and you multiply it, the result will also be in this like set of like floating point numbers, including not a number and infinity. Okay, and is multiplication is commutative? The answer is yes. And multiplication is associative. It's almost the same example. The reason why this is not associative is that we may lose some of the value depending on the order of computation. So these two expressions may result in different like values. Okay, so this one is a counterexample. So this one is no. So you have to pay attention to this like both like addition and multiplications are not associative. One is multiplicative identity, and the last one, this one is kind of unique. So this one is basically, the criteria for a commutative ring, whether multiplication, distributes over addition or not. And the answer is no, because this one actually shows like example when this result differ from this one. Okay, so again, this one is because of the overflow. If you think about, this case, we actually have very large numbers. Okay, we have very large numbers, 10 to the power of 20, and we multiply it, over, 10 to the power of 20th minus 10 to the power of 20th. Then in this case, this one actually cancels out each other and becomes 0, right? So eventually, if you multiply this number by 0, then the answer will be 0. But what about second case? In the second case, we actually expand, this original like expression to now actually have two terms, right? The first term here, second term here. So this one is A, B, C. Then this one will be A times B. This one will be A times C. Okay? But when you first calculate like this part, the first term, it will be 10 to the power of 20th by 10 to the power of 20th is really like a huge number. So let's say this one is like this one overflows, right? But in our like a floating multiplication, if it overflows, now it becomes what? Infinity, right? So it's now no longer like earthly value. It's like it goes to heaven, right? So it never comes back. So this one is now infinity. So infinity minus some like some other number will be basically also still infinity, right? Okay, by the way, this one is not really infinity, but this was infinity, this was infinity. So infinity minus infinity is not a number. We don't know what's the value. So this is not a number. So these two are not the same. So this concludes that this set is not commutative ring. And monotonicity rule also holds, except for infinities and nons. Okay. So let's cover the last part. 그럼 뭐가 되면 좋을까요? 인피니티하고 인피니티를 빼면. 0? 근데 사실은 우리가 수학적인 직관으로 봤을 때는 그게 맞지 않잖아요. 왜냐하면은 같은 인피니티만 인피니티가 있을 수, 말이 되는지 모르겠지만 하여튼 모든 인피니티가 같진 않잖아요. 네, 네. 그렇다고 만약에 B 패턴을 갖는다고 해서 그럼 제가 그러니까 지금 얘기하는 건 왜 그런지를 설명하는 게 아니라 왜 다른 게 더 이상한지를 설명하는 데서 좀 내가 입장이 곤란한데, 그죠? 제가 왜 이런지를 설명하는 게 아니라 왜 다른 게 더 이상한지를 설명하고 있잖아요, 지금. 근데 그렇긴 한데, 그래서 예를 들어서 막 0으로 하면은 그건 좀 진짜로 이상하죠. 오히려 나도 넘버는 뭐가냐면 약간 we don't know. 약간 그런 거잖아요. 나도 넘버라는 건 우리는 잘 알 수 없다. 그죠? 그렇게 선언하는 것이 조금 더 그냥 어떻게 보면 수학적인 우리의 직관에 더 가깝지 않나 그렇게 생각이 되고 아마 네. 네, 자동으로 나도 넘버가 돼요. 네, 하드웨어가 자동적으로 만약에 오버플로우가 발생하면은 그러니까 인피니티 마이너스 인피니티를 만약 하게 된다거나 이런 식으로 그러니까 나도 넘버를 발생시키는 조건을 로직이 가지고 있어서 그런 패턴이 들어오면은 결과가 나도 넘버로 나와요. 나도 넘버로 나오는데 네, 그렇습니다. 자, 이쪽 같은 먼저. 네. 그러니까 그게 어떻게 보면은 수학적인 의미에서의 오버플로우랑 인피니티랑 이 플로팅 포인트 리얼 임플멘테이션의 인피니티가 개념이 다를 수 있죠. 왜냐하면은 수학적인 의미의 인피니티라는 건 뭐냐면 우리가 어떤 숫자를 정해도 그 숫자보다 항상 큰 거잖아요. 어떤 우리가 파이나이트한 숫자를 정해서 찍어도 그 숫자보다 항상 큰 숫자. 그게 인피니티잖아요. 그죠? 무한 바운드가 안 되는 거죠. 그러니까 어퍼 바운드가 없는 거죠. 숫자에. 그죠? 바운드를 정할 수 없는 게 이제 그런 숫자인데 이 우리가 실제로 임플멘테이션하는 입장에서 여기서 나온 인피니티라는 거는 그런 수학적인 인피니티가 아니라 이 넘버 시스템이 표현할 수 있는 최대 숫자를 넘어가는 숫자는 다 인피니티가 되는 거잖아요. 그죠? 그러니까 약간 아까 얘기한 대로 이게 뭐냐면 계속 우리가 반복적으로 얘기하고 있는 abstraction, 그러니까 컨셉과 실제 구현상의 뭔가 미스매치라고 볼 수 있는데 구현으로 말하는 우리가 인피니티라고 하는 것은 최대 표현할 수 있는 값의 레인지를 넘어가면 인피니티가 되는 거고 수학적인 의미에서의 인피니티라는 건 아까 얘기한 대로 어퍼 바운드가 없는 거죠. 바운드가 없는 숫자. 그죠? 그러니까 조금 둘 사이에 미스매치가 있죠. 네. 네. 여기 구현에서는. 그러니까 IEEE 754 스탠다드에서는 오버플로우가 나면은 걔는 인피니티로 본다. 그렇게 되는 거죠. 네. 그래서 먼저 네. 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 그렇죠. 네. 만약에 두 개를 계산했는데 우리가 표현할 수 있는 숫자가 이제 디노멀라이즈 넘버는 되게 작은 숫자니까 상관없고 노멀라이즈 넘버의 맥스가 이제 표현할 수 있는 게 다 0이잖아요. 마지막 수 0일 때 근데 두 개 어떻게 보면 그런 숫자를 계산을 했는데 곱셈을 하든 덧셈을 하든 계산을 해가지고 했더니 이 익스포넨트의 값이 1 또는 그 이상으로 넘어가는 숫자가 나오면 이제 인피니티가 되는 거죠. 인피니티죠. 맞습니다. 네. 인피니티는 상수되면 인피니티고 인피니티를 0으로 나눠도 나도 넘버고 0으로 나눠도 나도 넘버 아니지. 인피니티 0으로 나누면은 저도 헷갈리는데 아마 인피니티일 거고 인피니티로 나누면 나도 넘버일 거고 상수를 0으로 나누면은 인피니티죠. 네. 맞을 거예요. 아마 제가 얘기한 게 정확하게는 그 스펙에 나와 있는데 아마 맞을 거예요. Okay, let's move on. So, so far we dealt with the general like arithmetic, how we represent the numbers, but we have to know for you to do your homework, you have to know this like how you use these numbers in C, right? Because that's a part of your homework. So C actually guarantees two level, like a floating point, like a float and double, like a single precision 32-bit representation or double precision 64-bit representation, right? Two numbers are supported. By the way, interesting these days, there's like a non-standard like implementation also support float 16. Like a float 16 is like called mini float. Mini float is like we only have like 16 bits, and float like 8. Even like a small like a floating point value this is particularly relevant for like a deep learning because in deep learning like network, they actually have it's very insensitive to the precision. You can we don't really need like that like many bits to represent a number. So in like a deep learning architecture, they actually introduce many custom like a number representation formats. For example, like Google TPU use like an 8-bit integer. They actually use like a fixed point operation. But in like Microsoft data center, like called Brainwave, they actually use like a 9-bit custom floating point format because that's kind of the optimal number of bits, minimum number of bits that are necessary to guarantee the correct operation. So this notation has a lot of implication in like designing hardware and especially for like these like deep learning algorithms. Okay, so see the two levels, float and double. Casting rule. You can cast like integer to float and float to double and so on. So if you cast like a double and float to int, then simply you truncate like this fractional part, right? Because you this like real number into like integer, then actually you simply cut off this like whatever follows the decimal points or binary points. So this truncates the fractional parts and like rounding towards 0. And it's not really defined if the number is either like out of range, like infinity or none. Then if you want to try to like assign this not a number to integer, to try to cast it, then the behavior is undefined. It's not defined. But in many cases, this value is generally like a t min, like the minimum number that can be represented. Into the double, because this one is you try to put this integer to real like a scientific number format. The exact conversion happens in this case as long as int has 53 bits or fewer like a word size. Why? Any guess? 그러니까 만약에 인테저 값을 리얼 넘버로 넣고자 하면은 값이 안 깨지는데 53비트 이내일 경우에는 안 깨지고 53비트 이상이면 깨지죠. So it means if you want to try to cast like this integer number, hold like integer value into using like this floating point representation, like a double representation, you don't lose any numbers until as long as you have like a 53 bits or fewer. But if you actually more than like a 53 bits, then you actually lose some value. Why? 맞습니다. Exactly, he's exactly right. Because we in like in double format, if you remember, sign bit, exponent, and like a fractional bits here, like this like exp fraction, right? Because this one was 52. So if you're like all like a valid digits can be held within this, then you don't lose anything. But if you actually have like more than like a 53 bits of like a valid digits, then you start losing some of the number, even though this one is integer. Okay. Okay. Float will round according to rounding mode, and this is summary. Any questions about the floating point? 네, 맞습니다. 예, 좋은 질문인데. 우리가 지금까지 얘기한 인트는 사실 32비트였죠. 32비트였는데 여기선 그냥 일반적인 그냥 인트라고 하지 말고 그러면은 그냥 롱롱이라고 생각하세요. not int, 롱롱. 이렇게 하면 되겠죠? 64비트 숫자. 인트는 우리가 지금 얘기했을 때는 32비트라고 얘기를 했었으니까 롱롱. Let's say this is long, 64bit. Okay, so. 네. 그렇죠. 플로팅 포인트 그 넘버 레프레젠테이션 있는 숫자인 거죠. 그러니까 그 플로팅 포인트 넘버의 셋에 들어가 있는 숫자죠. 물론 그 수학적으로 생각했을 때 그 값이 우리가 갖고 있는 뭔가 콘크리트한 값은 아니지만 그 레프레젠테이션으로 표현할 수 있는 값의 셋에는 들어가는 거죠. Okay, so let's come back to integer arithmetic. So I think we stopped right before, talking about right before the strings. We already talked about, I don't know if you guys remember or not, it's more like, we talk about big endian, little endian, all these issues, and pointers, and so on. So, let's finish. Let's talk about, how we can deal with strings in C. So, typically if you use like a C program, you use like a character array type, like char character array type to represent a string. In this case, we actually have we use like an ASCII code for like a character string, right, by default. So ASCII code, one character takes 1 byte. So in this case, we actually have like a 5 digits, so it takes like a 5 bytes, but we actually have like a 6, right? Because we actually need like one more bit, which is called terminator like symbol, which is represented by \0, right? So \0 is kind of terminator string, which signify actually this string ends here, right? So if you store this like in a string, let's say this one is the biggest starting address of S, like this one is the base address, then this one is the ASCII code for 1, this one is ASCII code for 8, this one will be ASCII code for 2, and so on, right? And it's followed by the terminator string, like null terminated. Basically, by seeing like this 0, 0, we know that, oh, this is the end of the string. Okay? And compatibility, there's no issue of like endianness because just 1 byte takes like 1 character, so there's no issue of this like endianness, which actually changes this order of bytes within a word. So there's no issue. So here are just C puzzles. I mean, let's go over one by one. So for each of these things, whether this statement is true or false, that's the question. Let's say in this case, x is like integer value, y is the another integer value, and ux and uy are tested like unsigned integer value. Okay, there are 4 variables, and the question is, this property actually holds or not. If x is minus 0, x is minus, then x times 2 will be always minus. Is it true or not? Almost true, but not always, right? When this property doesn't hold. When x is t-min, right? If x is t-min, what happens? It actually it overflows, right? Overflows and wrap around to the most positive number. So now, if x is t-min, like a minimum, like a negative number, then actually you end up getting the very, very, like a very, very large positive number. So this one doesn't hold in general. Second part, ux is always greater than, equal to or greater than 0. Yes, that's true. I'm gonna skip some of the things. It's kind of easy ones. I mean, xn like a 7. So this one means you actually do like a bitwise AND, right? So if you do this, because 7 is like 0, 0, 0, 0, only you have like a 3 ones in the last 3 bits, right? That's like a 7. So if you actually take like bitwise AND, that means you only leave the last 3 bits of your original operand, right? If x and 7 is 7, that means the last 3 bits of this x is all ones, right? Right? So because this one is, if you take the AND, all of this like a 0 part will go away. It will become 0, right? And if you only like the last 3 bits of this x will remain in the result. And if this one is 7, that means all of these 3 bits will be ones. So if you actually shift it by 30 bits, then it'll be negative value, right? Because if you lattice piece will be all ones, and if you shift it by like 30 bits, then you're gonna have like a sum like a 1, 1, blah, 1, 1, all zeros, something like this, right? So it'll be true. Ux is greater than, equal to, or minus 1. This one is actually not true because this one becomes very, very, if you actually compare like a like a negative, like a unsigned number with signed number, we first cast this signed number in unsigned, right? So this -1 becomes really huge, like positive number. So this one doesn't hold. So actually this one does unsigned comparison. So this one, now this one doesn't hold. If x is greater than y, minus y is always less than minus y. Is that true? The answer is no. Can anyone guess what, any example when this one doesn't hold? Yes. 하나가 t민이면, 그죠? 둘 중에 하나가 t민이면, in this case, let's say this one's tmin, and let's say this one's like another like negative number, not tmin. Let's say this is like a -2, something like this. And if you take the inverse, the minus, then this minus y becomes, again, this one becomes tmin. And this one will become +2. So because of a limited like number of bits, one property of 2's complement number is positive and negative number has different like asymmetric range, right? So if you take the -2 like a tmin, then it actually returns itself. It actually returns to the same number, like tmin. Because there's no corresponding positive number to tmin, right? So it actually returns to itself. So now this one becomes tmin again. Now this one doesn't hold. Okay? X times x is always greater than. The answer is no. What if there's overflow? Let's say you multiply like two very large x, then you actually end up having like overflow, then it becomes negative number, right? So this in general is not true. Let's skip some of them. It's too many. I've run out of time. Let me just go for the things. Which one is interesting? I don't know. We do some like a few more things. What about this thing? If x is minus, then minus is always plus or equal to 0. This one actually doesn't hold for tmin, right? As I said before, if you take the minus to the tmin, then it will become tmin again. So this one doesn't hold for tmin. What about this thing? The last one. If you take x and x minus 1 and bitwise AND to it, then it will be non-zero. So it's generally true, except for tmin again. Tmin is the headache because let's think about tmin here. Tmin is in bit representation it will be 1 0 0 0 0 0 0 0 0, right? And tmin minus 1. Tmin minus 1 is because you take like a -1, it will actually wrap around to become the most positive number, like tmax, right? So in this case, it will be tmin minus 1 will be 0 1 1 1 1 1 1 1 1, like tmax. So if you take the bitwise AND of the two, then it will become 0, right? You can also find that for any other value, this actually statement is true. Any other value, this statement is true, but only for tmin, this one doesn't hold. Okay, let's do it. So what if like x equals 1? That's good. That's good too. Either like a 0, one of the value is 0, or tmin. Otherwise, it will hold. Thank you for pointing out. 이게 말이 안 되네. 이게 x가 0이면 그냥 게임 끝이네. 그죠? If x is 0, then no matter what, just the output will be 1. Output will be 0, right? So either this one or this value will be 0, then it doesn't hold. So there are many some other cases too for pointing out. But anyway, this one doesn't hold. All right. So so we can apply these numbers to represent like a Boolean algebra. I hope you already have taken this logic design, so you know what is a Boolean algebra. But interestingly, this like a Boolean algebra is like a mathematical model for digital system. Okay, so if you actually have like a logic, like a circuit that can be very nicely modeled using like a Boolean, and vice versa. Once you have like a logical expression, like an abstract, like a logical model that can be easily mapped to like network of gates, right? So you can actually use like an AND gate, OR gate, NAND gate, and expression. So it's a very convenient way of expressing any like a logic, like a digital system. So this one is like based on like MIT master's thesis. This one is called like perhaps the most like influential master's thesis in the history, because in grad school, master's thesis is kind of, it's not really, it's kind of, the expectation is pretty not that high. But this one is really like a very impactful master's thesis, perhaps in the history of computer science and engineering. Basically the idea was reason about this network of relay switches, whether they are connected or not. If these two terminals are connected, then this one is encode this connection as 1, and it's open. Open means not connected. Then this model the switch as 0. So in this example, either connected or B is not connected, then or A is not connected or B is connected, then this like entire two terminal will be connected. So you can represent these two terminals are connected when either A is connected and B is not connected, or A is not connected or B is connected. Right? Either of these conditions is satisfied, then we know that this is these two terminals are connected. Otherwise, it's connected. And you say A XOR B, right? And binary number property, I don't know, it's kind of odd position, but the claim. So in binary number, we know we add all of the numbers, all of the bits, then the maximum number that can be represented is represented using this sigma, I equals 0 through W minus 1, and we add like a 2 to the power of I. Then some of this number will be, this number will be 2 to the power of W minus 1, right? That's the maximum positive number that we can represent. And we can prove, using like mathematical induction. I don't know, you already learned mathematical induction in high school. 요즘도 고등학교에서 수학적 기납법 같은 거 가르치죠? Mathematical induction, 프루브하는 거, 그죠? So if you apply mathematical induction, this one actually holds when W is 0, and if you assume this one is true, this property is true for W minus 1, and we can show, this property also holds for W, right? So that's the basic idea, but it's kind of, odd position, but, So let's think about, very interesting real case when this, dealing with string can be very tricky, okay? Especially if you're interested in like a computer security, many of these like bugs or worms are built on this program's vulnerability, okay? In a sense, your original program has some sort of concealed bug, okay? And the attacker exploit this concealed bug to some malware or whatever code you want to execute. So this one is very simple example of buffer overflow type of attack. So let's think about this function. So there's a function called copy from kernel. This one actually is based on like a real operating system code, like real OS code. So in your OS actually provides some like interface to copy some value from the kernel space into the user space. I don't know, because you guys didn't take OS. You can think of it as like some sensitive data to like insensitive data region. So let's say there's some if you have like memory space, there is some region called like kernel region. So this one is very like sensitive space because it manages the entire system. So you can, you only access part of this like region only through the well-defined interface. Okay, so let's say there's some like a buffer inside the kernel. So this is a kernel buffer. Here, let's say it's kbuff. Kbuff is the some buffer inside the OS kernel, and actually the kernel actually has so many like sensitive data, and this function like copy from kernel actually is the interface like function that you can use to copy this like a value of this buffer into your like user level space. Let's say there's another buffer called like mybuff. So what you want to do, using this function, you want to copy this sensitive into your your like program like space. So this one is done by using like invoking this copy from kernel function. So this is similar code. Find FreeBSD's of get p name. This is kind of OS like a function, and how you can exploit this one to do something like malicious. So here is an example. So this one is like a typical use. Typically, what in your user level code, you first allocate some buffer, like let's say character array here, like mybuff, as I've shown you. Let's say you allocate your buffer in your user space, and you call this OS function, like a kernel function, copy from kernel. Then it actually reads the value from this like kernel buffer and copy those value to user level, like a user space, and you print the value. That's what it does. This is typical usage. Okay, but if you want to do like exploit this maliciously, then what you can pass this minus value. Okay, so what's going to happen then? So this minus m size is really like a big positive number because as you know, if you do see the function signature, this is like an unsigned number. But let's say you provide some like a negative number, then generally this number becomes really like a huge positive number, right? So the problem in this code is that originally you intended to only copy like some of this like a very limited region of kernel space. But if you actually provide this large number, then you end up getting entirely dumping entire kernel space into the user space. That's what's happening, right? So this one is kind of example, how this number conversion can be problematic because by exploring this kind of vulnerability, you can access some arbitrary in the kernel space. Okay, that's the problem. And there are many these kind of attacks called like buffer overflow, format string. All these things are based on this kind of pointer schematic. Kind of common types of security attacks. I mean and mathematical properties. Again, we come back to the mathematical property of this like modular addition. Let's think about unsigned like add first. Hopefully you already know what's an abelian group because I already introduced the concept. There are 5 properties: commutativity, associativity, additive identity, and inverse. They all hold. So in other words, this modular addition, like unsigned modular addition, an abelian group. Okay, so basically, all 5 properties hold. What about T-add? Like the addition, like a T-add. By the way, the T-add is actually forms like isomorphic group to unsigned add. What it means is that let's say you have like 2 sets or 2 groups. And then if there's like a one-to-one correspondence, let's say you have like an operator, you can define an operator that sets up like one-to-one correspondence between these 2 groups, like elements between the elements within these 2 groups, then that's called like isomorphic. Okay? 우리말로 하면 뭐 등방성이라고 하나? 뭐 하여튼 isomorphic. So in other words, there is element-wise there's a one-to-one like a mapping between unsigned add and signed add. And then if they let's say, and there is like a mapping function between these two, well-defined mapping function between the two groups, then that's called isomorphic group. And also, likewise, this two's complement, because it's isomorphic to like unsigned like addition, the two's complement, like this, like a signed add, also forms like a group, like a abelian group, because there's a one-to-one correspondence between the two. Okay, so that's the property of integer addition. So if you characterize like a t-add, let's think about when what are the acceptable values. So let's think about like signed addition. Like let's say we take like two numbers u and v, and we divide this range to the positive u and negative u and positive v and negative v, right? Then these like white boxes are when there's no overflow. So this is kind of we don't lose any information here. But if you actually add like two positive numbers here, then there's some region when we actually have positive overflow. So it's kind of wrap around and to become the most negative number, right? So in this case, this one actually corresponds to this region. So in signed add, if u plus v is greater than t max, then actually it wraps around and becomes the most negative number. So you actually take this 2 to the power of w, take off this 2 to the power of w to the result. And likewise, if you actually add like two negative numbers, then we may actually have negative overflow, so that we actually have to add this 2 to the power of w to make it the most positive number. It's a wraparound, right? So that's what this figure actually shows. So negation is we have number of x. What's the easiest to calculate minus x in two's complement? Let's say I gave you a thing and ask you to calculate the negative x. What's the easiest way to do it? In logic design course, probably you guys learn it. 어떤 숫자의 2의 보수를 구하는 가장 쉬운 방법은 뭐죠? 가장 보통 맞아. 다 바꾸고 2를 넣으면 되죠. 그러니까 원래 값에다 다 bitwise를 취한 다음에 거기다 플러스 2를 더하면 되죠. So you can the easiest way to calculate two's complement is you invert every bit, and then you take plus 1 to the result, right? So that's how we calculate this minus x. So here, so if you take the number, any number, and its complement, and you add them to, then you end up always getting like minus 1. 그죠? 하나의 원래 bit이랑 그 bit에 invert된 모든 bitwise not 된 bit을 더하면 항상 1이겠죠. So if you take these add two numbers, regardless of the value of x, it will be always minus 1, right? So in the example, let's say we assume like a 16-bit number representation, x equals 15,213. And if x is the original number, and if you take the not value, I mean the bitwise not to apply bitwise not to the original value of x, then it will be minus 15,214. And if you add 1 to it, then that will be you recover the original value, but in different polarity. Positive becomes negative, and this is basically how we calculate the negative value of x. And complement and increment. So if it's 0, and if you take the increment, so how let's think about the minus. Assuming the original value of x is 0, then if you take apply the bitwise not to this original number, then all bits will be 1, which is minus 1, right? So if you add 1 to it, then you recover the original value of 0, right? So that's how this two's complement works. Interesting case is this again. This is if x is t-min, minus x is still x, right? As we talk about this problem, when I talk about when you solve this integer quiz. So here, have x here. Minimum number t-min will be obtained by setting MSB 1 and the remaining bits to 0. And if you take the bitwise like inversion, then it will be 0, 1, 1, 1, 1, 1, 1, and so on. And if you add 1 to it, then basically you recover the original value. Okay? The reason was because there's no corresponding positive number to t-min, right? So that's the reason why if you calculate the 2's complement, you come back to the original number. Okay? It's kind of canonical counterexample to. So how this number compiles? I mean, we're going to talk about more about this like x86 assembly language in the following lecture. But let's take a look how this code is converted. So first we compile this function. Let's say we want to compile this function, calculate the x times 12 and return this value, right? So it's basically very simple function that takes a value x and multiply 12 to it multiply that number by 12 and then return the value, right? That's what it does. And if you compile it, this one makes very weird code, but this one is actually very efficient code. The reason was instead of using like a general like a multiply instruction, it only used shift and add. Okay, so instead of like a general like a mul instruction, mul is like a multiply, which is much more expensive than this like a shift and add. So this one actually generates like this 2 instruction code. In the first case, this one is called load. This one actually calculate the constant value. So this one is notation. By the way, you don't really have to worry too much about this notation at this point. But what this one does is, let's say you have like some parentheses and some like a register B followed by register I followed by some constant like S. Okay. Then what this compiler does is it calculates the value of RB plus RI times S. Okay, so this is actually compiler. Actually instruction does not compiler. The CPU actually compute this value whenever it sees this like expression. So in this case, what it does is, let's say RAX actually holds like a value of x. Then what it does is, it first computes RAX plus RAX times 2, and store the result to the register RAX, back to itself. So it actually update the value of itself to x plus x times 2, which is like 3x, right? So once you compute the 3x, now you can apply shift to instruction. So this is like a shift left. Shift to left by 2 means like a multiplying by 4, right? So you compute shift left like this value by 2 and store the result back to the RAX register. So this one basically effectively computes x times 12 without using like a multiplication instruction. Okay? So don't 여기서요? 왜냐하면 요거 그냥 한 명령어에서 저거 하나만 쓰면은 그냥 알아서 얘가 다 이렇게 계산을 해줄 수가 있거든요. 그러니까 명령어를 세이브하기 위한 거죠. 가장 명령어를 적은 수의 명령어를 멀티플라이를 쓰지 않고 가장 적은 수의 명령어로 이 x 곱하기 12를 계산할 때 이것도 내부적으로는 뭐 시프트로 계산이 될 수 있죠. 네. 근데 어쨌거나 그냥 이 식의 의미는 요 가로친 식의 의미는 앞에 2개의 레지스터를 인풋으로 받고 3개의 컨스탄트 값을 인풋으로 받아서 이거 더하기 이거 곱하기 이거를 항상 계산한다. 컴퓨터가 하드웨어가 계산하는 거예요. 근데 이 내부적으로 이 곱하기를 실제로 일반적으로는 시프트로 하겠죠. 이게 아마 S가 2의 n승으로밖에 아마 세팅이 안 될 거예요. 제가 기억하기로는 S가 2의 n승으로밖에 세팅이 안 돼서 아마 시프트로 다 내부적으로 연산을 할 거예요. 네. So the second example is, don't worry too much about these instructions because I'm going to explain what this instruction do in like the next lecture. So you don't have to worry too much about what these instructions do. But that's kind of example. And the second example is like a div by 8. So let's say in this case we actually have unsigned number, like we say unsigned long, like unsigned number, and it returns, divide this number by 8. So the easiest way to implement is we should shift this number to the right by 3 bits. Okay, so that's the it's like it uses like a logical shift for like unsigned value. I mean, for unsigned value, we basically use like a logical shift. I mean, logical shift and to be precise, for unsigned number, logical shift and arithmetic shift are the same, because that's not true. Yeah, actually that's not true. So we for unsigned number we use logical shift for division. 그죠? 왜냐하면은 because in unsigned number there's no negative number, right? So whenever you actually divide it, you always have to pad this like upper like n bits with 0 instead of 1, right? So we actually use like a logical shift for unsigned number, but in contrast, if you actually take this like a signed number, so this is signed. For signed number, you actually have to use this like arithmetic shift, because it may be negative. So this one is basically there are two like shift instructions. This is SARQ. This one is arithmetic shift. In contrast, in the previous page, this one is like a logical shift. Okay, there are two different instructions depending on whether you deal with you do like a logical shift or arithmetic shift. And this part, for arithmetic, for signed division, we actually do some fix, add a minus +7 if the value is 0. Less than 0. We do this because for positive numbers, you can simply just shift to left by 3, right? That's good enough. But for negative numbers, we actually have to do some adjustment because we want to make sure that the remainder should be always positive. When you actually calculate this quotient and remainder, the remainder must be always positive value, right? So if you want to divide some negative value by 8, then you first add these two, add a 7 to this value, and then you divide it, so that you basically, in effect, this one should add 1 to your quotient value. Okay? 이게 무슨 얘기냐면은 so many puzzle face. But okay, so sorry, time is up. So I'm going to start from here next time. So with this one, and then we're going to move on to chapter 4 about instruction set architecture. Okay.